Let's first look at the approach that we took towards building this prediction model. The approach that we took is aggregating and synthesizing data from multitude of sources, which includes encounters, diagnosis, vitals, pharmacy, labs and members. From this data we attempt to understand the mechanism of the disease, which is to identify all the drivers associated with how the disease becomes expressed in an individual. With this mechanism and the prior history of the patient, we then try to determine the risk profile, which will allow us to identify the risk candidate and the degree of risk. The data we used was from 2016 to 2018, and it was from a single marketplace of around 139,000 patients, with around 539,000 encounters, having around 168 providers in the mix. What you see on the left-hand side is a distribution of the encounter mix to provider specialties, and what you can notice here is a richer percentage of the encounter mix that is related to family medicine and cardiology, while the other diseases are also fairly represented. The reason we picked this dataset is because it well represented the first interaction of a patient with caregivers that could be deterministic of diabetes diagnosis. Here is some factual understanding of the training data. As mentioned earlier, we have 139,000 patients with around 539,000 unique encounters. Out of these 139,000 patients, we could determine a little over 50% patients had greater than 3 visits encounters, and around 11% of these population had lab information. We were able to build around 100 clusters having around 715 patients per cluster that was used in building and validating the model. Another data fact is that we had 10% of the patient population in this dataset with diabetic diagnosis. As part of the cleansing process, we had to remove those encounters that didn't have any diagnosis code as they were simply noise. The outliers were also removed for those encounters that had mischaracterized vital information, such as temperature, weight, etc. Special characters were also removed in the data we had as part of the cleansing activity. From an imputation standpoint, we had to calculate values, such as BMI, through the weight and height data that was available, and also create activity sequence, such as sequencing the encounters when the subsequent visit date was missing, and make sure the data was legitimate and as per the requirement for building the prediction model. Here let's look at the approach that we took for the model development and validation. As stated earlier, the key data inputs were encounters, diagnosis, vitals, pharmacy, labs and members from the patient data. The data was populated into a Postgres database, and from there we extracted patients that had greater than 3 visits, and then the data was prepared and cleaned as explained earlier. Next, we worked on shaping the feature data into a 3D frame. Also, the predictor variable was defined using 2 of the historical visits to predict the next visit. Model approach analysis. Working on broadly 2 approaches GBM and LSTM with Bayesian and Gaussian processes. The variable selection was done in the embedding layer based on the significance of the variables that were driving the predictor values for the diabetes. Within the data itself at the input layer we had 43 variables, 32 of those were determined to be significant features, and from that we built it into an LSTM model with a 30 neuron step. 80% of the data was used building the model, and 20% was held for prediction validation. The validation of the model was done with the held dataset to make sure the model can accurately determine the likelihood of diabetes being diagnosed in the patient's next visit. The AUC value for the model that we built got represented at 0.847, using about 1% of the data, and this value increased significantly when we ran with 25% of the data. Now let's go through on how the data frame is constructed. As mentioned earlier, the 3D construct is built based on the 2 prior visits where the vitals data and the diagnosis data for a patient from 2 separate encounters are considered. These 2 sets of data are then transformed into rows with 2 separate encounters that include both vitals and diagnosis, which is converted into 3D frame which is used for analysis. Also, you would notice a last column in this dataset highlighted in red color on the right-hand side, which provides an ability for us to say whether this visit was diabetes related or not. Once the frames for those 2 visits are set, we then look at the embedded features and input that into the LSTM model to predict in the next visit. Here you can see the output of the prediction model. What you see here is all the iterations that we went through to determine the number of neurons, epochs, embeddings and the batch sizes to ensure that we have the right bias and variance within the model. If you look at the result tables, we went from 0.847 to 0.888 as we increased the training size to 25% of the overall data. NTT data focused on highly accurate prediction of the onset of type 2 diabetes. We investigated whether prediction accuracy can be improved by utilizing lab test data obtained from health checkups and incorporating health claim text data, such as medically diagnosed diseases, with ICD-10 codes and pharmacy information. Now let's look at the demonstration to see how NTT data's prediction analytics helps to predict onset of type 2 diabetes.